Okay, good morning, everyone. We're going to start our class today. All right, let me move this over here. All right, today we're going to start a new topic, which is NP and NP completeness. Okay, everyone can hear me, right? Just want to double check. Yeah, is the audio, can somebody just tell me if the audio is working? Okay, great. Excellent. All right, so we're going to start this new topic about NP and NP completeness. And so let me just introduce this topic. It's actually very important in computer science. Okay, so the basic question we're trying to answer is that how efficiently can you solve a problem? Okay, so if I give you some sort of problem, can you come up with an efficient algorithm to solve that problem? So basically, the study of algorithms, at least sort of in the modern sense of algorithms, goes back to something like the 1950s. Okay, so the first computers were developed basically in the 1940s, and then in the 1950s, people started developing algorithms similar to the ones that we have today. And so as they studied different problems, they noticed that for some problems, you can actually solve them quite efficiently. Okay, so for example, for sorting, right, you can sort a bunch of numbers efficiently. Okay, or for max flow, you can compute a max flow pretty efficiently. But then they also noticed that there are other problems where there doesn't seem to be any sort of efficient solution. Okay, the only solution seems to be some sort of brute force solution, which basically tries all possible answers. Okay, and usually there are many, many possible answers. So for those problems, there's no efficient algorithm. And so then people started thinking, for these brute force problems, is there some more clever algorithm that we can come up with to solve them not in the brute force fashion, but in some sort of efficient fashion? Okay, and so it took a long time for people to sort of develop a systematic way to think about this problem, even. Okay, so it's not, so we're trying to figure out which problems are efficiently solvable versus not efficiently solvable. And even to ask this question in sort of a mathematically rigorous way, you need to develop some machinery for that. And it took, about like 20 years for people to do this. Okay, so around like 1970, people finally found a sort of a very systematic and rigorous way to study this problem of efficiency, which is the study of NP and NP completeness. Okay, and so that's what we're going to talk about today. And so I should just mention that even though this theory of NP completeness is a way to look at the complexity of algorithms, we still don't have many good answers in terms of whether or not we can solve problems efficiently. Okay, so NP completeness provides you a framework to talk about this problem, but it doesn't solve the problem. Okay, we're still trying to solve the problem, and we're actually probably pretty far away from actually solving this problem. Okay, so I'll talk more about that later. Yeah. Okay. Yeah. So anyways, so the problem we're trying to figure out is what is the fastest way to solve a problem? Okay. So for example, we looked at sorting, and we know that if you use something like merge sort, you can sort n numbers using n log n operations. So then the question you could ask is, can I do better? Okay. Can I maybe use only order n operations? Okay. And it turns out that for the sorting problem, you can actually prove that you cannot go faster than n log n if you restrict yourself to this to a special model of computation, okay, called the comparison model. Okay. But in any case, for the sorting problem, we can actually prove that you need n log n time in certain models of computation. Oh, what is this saying? All right, so I don't know what that says. All right. Okay, but what about for other problems? Okay, so for sorting, we have the right answer. We have an algorithm which takes n log n time, and we can prove that this algorithm is optimal. Okay, what about for other problems? Do we have optimal algorithms for other problems? Okay, so for example, you can look at this problem of coloring. Okay, so the coloring problem is basically, suppose I give you a map. Okay, so a map is basically a bunch of like regions, right? And the regions cannot overlap with each other. Okay, so for example, a world map, right? You have a bunch of countries, which are the regions, and the countries don't overlap, right? But the countries can touch each other, okay? So the coloring problem is that if I give you this map, then I want you to give a color to each country such that if two countries touch each other, they get different colors. Okay, so for example, here you have like China and Russia, right? And so they have a border, and so they touch each other on the map, and so they need to have different colors. Okay, and likewise, like this China and Mongolia over here, right? They also share a border, so they need to have different colors. Okay, and then Russia and Mongolia also share a border, so they also need to have different colors. Okay, so just for like these three countries over here, we need to have like 3 different colors. Okay, so now suppose you're trying to print this map, then you want to use as few colors as possible, right? So that makes your printing cheaper. Okay, so then your question might be like, what is the fewest number of colors I can use in order to color some map? Okay, and now it turns out that there's this thing called the 4-color theorem. Okay, and it says that given any map, okay, you can always color it using 4 colors, such that adjacent regions have different colors. Okay, so any map, you can do it with 4 colors. Okay. So therefore, if I ask you a question, so I'm going to give you a map, okay, and I ask you, can you 4-color this map? Okay, so then there's an efficient algorithm to solve this problem, because you're guaranteed that you can 4-color this map. Okay, so your algorithm simply says, yes, I can 4-color the map, because I know by the 4-color theorem that it's always doable. Okay, so this is a very efficient algorithm, right? In fact, you can say that the algorithm has like 0 time complexity, because you don't even need to do any computations, right? You just output yes. Okay, yeah. So there is an efficient algorithm for the 4-coloring problem. Okay, but what about? But sometimes you see on this map you can use only 3 colors, right? So then what if I give you the map and I ask you, can you color the map using only 3 colors? Okay, so now you might need to use a different algorithm. Okay, and it turns out that once you try to color using 3 colors, we don't have any efficient algorithms to determine whether or not it's possible to color using 3 colors. Okay, in fact, if I give you like a map with like n regions, okay, then basically the only way that we have of determining whether we can use only 3 colors instead of 4. Okay, the only algorithm we have is some sort of brute force algorithm which tries all possible colorings, right? So then if you have n regions and you have 3 colors per region, then you have like 3 to the n possible colorings. And so the algorithm that we have right now, the best algorithm, is basically to try all 3 to the n possible colorings. Okay, I mean there's some improvements on this algorithm, but it's not. But in the end, we still have to try many possible colorings. Okay, and so this algorithm is very slow, right? Because if you take 3 to the n, right? So there are like about 200 countries in the world. So if you take 3 to the 200th power, that's like it's a huge number of colorings. Okay, so you have to try like a huge number of possible colorings. So basically, for the 4-color problem, we have a super efficient algorithm. Okay, it just outputs yes always. Okay, and for the 3-coloring problem, we need exponential time to do this. Okay, so yeah, so that's the question we're trying to answer. Okay, so is there some sort of why is it that for 4-coloring it's so easy to determine, and for 3-coloring we need exponential time? Okay, do we actually need exponential time? Can we go faster? Right? Because it seems like we changed the problem by such a tiny amount, so maybe there should be some efficient algorithm for 3-coloring also. Okay, but the problem is that nobody knows of any efficient 3-coloring algorithm. Okay, and furthermore, almost everybody thinks that it's not possible to find an efficient 3-coloring algorithm. Okay, however, it's also the case that nobody can prove we cannot find an efficient algorithm. Okay, so basically everybody thinks we cannot efficiently 3-color. Okay, but nobody can prove this fact. Okay, so the theory of NP completeness, which is what we're going to talk about for the next few lectures. Okay, it's basically a mathematical framework to try to answer questions like this. Like, can we efficiently solve certain types of problems for which we only have brute force algorithms right now? Okay. Yeah, and as I said, it's not a it's a very useful framework, but we don't have too many answers yet. Okay, so in fact, the study of NP completeness has led to a number of many interesting questions. But for many of these questions, or for most of these questions, we actually don't have answers to them. Okay, so right now we have more questions than answers. Okay, but what I'll do is I'll introduce the basic this framework that we have. Okay, and to do that, I'll talk about these things called P, or these are called complexity classes. Okay, so I'll talk about the P, NP, and NP complete complexity classes. Okay, and then we'll also see how we can use these complexity classes to try to answer this question of whether we can design efficient algorithms. All right, so yeah, so we're going to focus on these three classes, P, NP, and NP complete. Okay, so let me start with the class P. Okay, so yeah, so first of all, let's define what a polynomial time algorithm is. Okay, so a polynomial time algorithm is any algorithm which runs in n to the k time for some constant k when your input has size n. Okay, oh, sorry, so I should have an example over here. All right, yeah, so as an example of this, right, so if you consider like matrix multiplication, okay, so that takes like, let's say, n cubed time. Okay, if you just use naive matrix multiplication, it takes n cubed time, and so this is a polynomial time algorithm. Okay, another polynomial time algorithm is like sorting, right, that takes n log n time, and so that runs in basically order n, it's less order n log n is less than n squared. Okay, so therefore, sorting also runs in polynomial time. Right? Again, n is the size of your input. Okay, so for example, for matrix multiplication, it might be like the number of rows or number of columns that you have. Okay? So sometimes for some problems, you have like different ways of defining what your input size is. Right? So for example, for matrix multiplication, you might want to define your input size as the number of total entries that you have in the two matrices you're multiplying. Okay, instead of, let's say, the number of rows or number of columns. Okay, so there is sort of like some ambiguity in how you define the input size. But it turns out that for the types of problems we care about, no matter how you define the input size, as long as it's some sort of reasonable definition, okay, then if an algorithm has a polynomial time, if a problem can be solved in polynomial time using one definition of input size, okay, then it can also be solved in polynomial time using some other reasonable definition of input size. Okay, so usually it doesn't matter how you define the input size, as long as you use some sort of reasonable definition. All right, so anyways, yeah, so that's what polynomial time algorithms are. And now P is a collection of problems, okay? And P includes all of the problems which can be solved in polynomial time. Okay, so if you have any problem, and if it's possible to find a polynomial time algorithm to solve that problem, then that problem belongs to P. Okay, so for example, matrix multiplication belongs to the set P, right? Because there is a polynomial time algorithm to solve matrix multiplication. Okay, likewise, max flow belongs to the set P because there is a polynomial time algorithm to solve max flow. Okay, for this coloring problem, this three coloring problem, well, for four coloring, okay, so this belongs to the class P because, there's a constant time algorithm to solve that problem, okay? But for three coloring, okay, we don't know whether three coloring belongs to the class P because currently we have an exponential time algorithm to solve that problem, okay, and we don't currently have any polynomial time algorithms to solve that problem. But that does not mean that it's not possible to solve it in polynomial time. Okay, maybe some very smart guy one day is going to come up with a polynomial time algorithm to solve three coloring. Okay, if that happens, then we know that three coloring is in the class P. Okay, But right now, we don't know whether it's in P or not. Okay, it could be in P, it could be not in P. Yeah, okay, so these P problems, okay, the set of these problems P, okay, so these are called efficiently computable. Okay, and it's because we consider any algorithm which runs in polynomial time to be efficient. Okay, so now in practice, you might argue whether these polytime algorithms are truly efficient or not. Okay, because for example, if you have an n cubed time algorithm, okay, then this is actually a pretty slow algorithm, right? Like if you have n equals 1,000,000, then n cubed is basically you need a supercomputer to solve a problem, of 1,000,000 cubed size. Okay, yeah, and in fact, even if your algorithm takes like n to the 100th power, okay, by the current definition, this would still be considered efficient. Okay, even though in practice, if you have an algorithm which runs in n to the 100th power, it definitely is not efficient. Okay, it's going to take a huge amount of time. Okay, but nevertheless, because we're trying to go for we're trying to develop a clean mathematical way to talk about these problems, then we're going to say that as long as you can solve it in polynomial time, any polynomial, okay, we're going to consider that to be efficient. Okay, on the other hand, if you have a problem which takes more than polynomial time, okay, so remember little omega means that it takes strictly more than n to the k time for any constant k, then we consider this problem to not be efficiently solvable. Okay, so for example, if you have an exponential time algorithm, right, or if you have something that takes like n factorial amount of time to solve, that would not be considered efficient. Okay, so that's why this three-coloring algorithm we have, right? So we consider this not to be efficient because it takes 3 to the nth power to solve. Okay, and in fact, 3 to the nth power is much slower than something like n cubed. Okay, so or any polynomial. Okay, so for example, if you take n equals 10,000, right, then n cubed is like 1,000,000,000,000, which is not too bad. Okay, that you can run 1,000,000,000,000 operations. But 3 to the n would be this massive number, and this number is just way too much for any kind of computation. Okay, it's more than like the lifetime of the universe times the number of atoms in the universe, for example. Yeah, so that's why we consider these exponential time algorithms to definitely not be efficiently solvable. Okay, so that's the class P. Okay, so next we're going to talk about the class NP. Yeah, and then P stands for polynomial, okay, because it's polynomial time. So now NP stands for non-deterministic polynomial time. Okay, so I'm not going to go through this term non-deterministic. Okay, so there's actually several ways to look at the class NP, and one of the ways is using this sort of idea of non-determinism. Okay, but that's kind of a little abstract or something. Okay, so instead, I'm going to talk about a different way of looking at NP. It's exactly mathematically equivalent, okay, but it's kind of a different perspective, which is somehow more intuitive, I think. Right. Okay, so before we talk about NP, I'm going to define some terminology. So, so the first one is that if you have a problem, okay, then an instance of the problem is just one particular input for the problem. Okay, so for example, if you have the sorting problem, right, then if I give you a set of numbers to sort, that would be an instance of the sorting problem. Okay, or if I'm trying to solve this single source shortest path problem, okay, then an instance of this problem is that I would give you a particular weighted graph, okay, and a source node, and then you have to solve the shortest path problem on that graph from that node. Okay, so then, so then P, we can say, is the class of all problems where for any instance that you get, okay, you can solve that instance efficiently in polynomial time using some algorithm. Okay, and now NP, okay, NP it's again a class of problems. Okay, so P is a collection of problems, and NP is also a collection of problems. But for NP, we're not asking you to solve these instances in polynomial time. Okay. Instead, you're supposed to do something called verify the instance in polynomial time. Okay, and I'll tell you what verify means in more detail later. But basically, you're trying to verify whether a problem is, whether an instance is solvable or not. Okay. And the way that you do the verification is that you need to have a verifier algorithm. Okay, so whenever you show that, so if you want to determine whether a problem is an NP or not, then first of all, you need to design a verifier algorithm for that problem. Okay. However, this verifier algorithm doesn't just work by itself. Okay, it needs some additional information in order to produce the output. Okay, and the additional information it needs is what's called a witness or certificate. Okay, so I'll go through this more formally later. But basically, to show that something is an NP, you need to design a verifier for it, and the verifier needs to have these things called witnesses or certificates. Okay, these are the same thing. Okay, witness and certificate mean the same thing. Yeah, and so let me just sort of go through this. Yeah, okay, so the verifier is going to have these properties. Okay, so this so for each NP problem, you need to design possibly a different verifier. Okay, and this verifier has to satisfy certain properties. Okay, so so the verifier takes two inputs. Okay, the first input is this instance X of the problem you're trying to solve. Okay, and the second input is the certificate. Okay, and we're going to call that Y. And the verifier, its output is just accept or reject. Okay, so basically, accept basically corresponds to saying that this instance X is solvable. Okay, and reject kind of corresponds to saying instance X is not solvable. Okay, so the verifier just tells you whether X is solvable or not using the certificate Y. Okay. So now the way this works is that suppose your problem X has a solution. Okay, so we're going to see some examples, but basically we have problems where either they do have a solution or they do not have a solution. Okay, and we're just trying to figure out whether X has a solution or not. We don't even need to figure out the exact solution. Okay, we only need to figure out whether or not it has a solution. Okay. And so in the first case, X does have a solution. And in this case, if you give a good certificate to this verifier, okay, then the verifier will output accept. Okay, but if you give like a bad certificate to the verifier, then the verifier could either output accept or reject. Okay, but the requirement is that when X has a solution, then it's always possible to find a good certificate, and this certificate will make the verifier output accept. Okay, so that's the first case where X does have a solution. And the other case is where X does not have a solution. And in this case, the verifier is going to reject, is going to output reject, no matter which certificate you give it. Okay, so any certificate, the verifier still is going to output reject if X does not have a solution. Okay, so that's so basically the intuition for this is that the certificate Y, it indicates whether X is solvable or not. Okay, so for example, Y can just be a solution to X, right? The verifier is trying to figure out whether X has a solution or not. So if I give a certificate which is equal to the solution for X, if I give that to the verifier, then the verifier can just see that this is a correct solution, and it will output accept. Okay. Okay. So, but on the other hand, Y doesn't have to be exactly the solution to X. Okay. Y can also be some sort of more abstract or indirect representation of a solution. It doesn't just have to be the solution itself. Okay. It can be some sort of indirect indication that there is a solution. Okay. So I'll give you an example of this a bit later, where Y is this indirect representation. Okay, yeah. So we have this verifier, and as long as you give it a good certificate, okay, then the verifier can check whether or not X X is solvable using the certificate. Okay, so that's the first property for the verifier. And then there's one more property, which is that the verifier itself has to be efficient. Okay, meaning that the verifier has to run in polynomial time. Okay. Yeah, the verifier, for example, cannot run in exponential time. Okay. we require that the verifier itself be fast. Okay, so this is still not the formal definition. So now I'm going to give you a formal definition for the class MP. Okay, that was just sort of the intuition for how to think about this. Okay, so for the formal definition, we need another to define another term, which is a decision problem. Okay, so a decision problem is just a problem where there's a yes or no answer. Okay, so for example, if I give you a graph, okay, then a decision problem on this graph is, does there exist a path from a node S to T? Okay. It's just yes or no. There is a path or there is not a path. Okay, I'm not asking you to find the path, right? You just have to say that there is or is not a path. Okay, or for example, another decision problem would be if I give you a map. Okay, is it possible to three color this map? You don't have to give me the three coloring. You just have to say whether or not it's possible. Okay, and one last example is if I give you a number. Okay, is it a prime number? Okay, you just have to tell me yes or no. Right, so now given a decision problem, okay, you can split, so this problem, you can give it different instances of the problem, right? Like I can give, for the prime problem, I can give you different numbers, right? Some numbers are prime, some numbers are not prime, okay? So then some of these, we're gonna say that the yes instances are the instances where the answer to the problem is yes. Okay, so for example, for the prime problem, if I give you the instance 11, right, then because 11 is a prime number, then this is a yes instance of the prime problem. Okay, if I give you another instance 10, then 10 is not a prime number, so this is going to be a no instance of the problem. Okay, so we're just going to divide all the instances into the yes instances and the no instances. Okay, so now, given these two definitions, we can define what the class MP is. Okay, so now suppose you have a decision problem A. Okay, then we're going to say that a polynomial time verifier V for this problem A, okay, is an algorithm that has the following properties. Okay, so V is a verifier, and V itself is an algorithm. And we require this V algorithm to have the following properties. Okay, so first of all, V's input. Okay, this is going to be an instance. So V is going to have two inputs. So the first input is going to be an instance X of A, okay, of the problem. Okay, and the other input is going to be a certificate Y. Okay, so Y is just some sort of string, right? It can be like a binary string. Okay. All right, and then the verifier's output. Okay, so when I give you X and Y as the input, the output is just 0 or 1. Okay, so 0 represents reject and 1 represents accept. All right, and now suppose this instance of X of A, suppose X, right, is a yes instance. Okay, meaning that X does have a solution. Then what we require is that there has to exist a Y which can make V output 1. Okay, so there exists some Y such that V on the input X and this particular Y, then V is going to output 1. Okay, this is when X is a yes instance. And when X is a no instance, okay, then we require that for any possible certificate Y, V is always going to output 0. Okay? Yeah, so again, when X is a yes instance, there exists a Y to make V output 1. And when X is a no instance, then for all Y, V is going to output 0. Okay, and then lastly, V needs to run in polynomial time. Okay, V needs to be efficient. Okay, and finally, this class MP. Okay, this is a set of all decision problems such that there exists a polynomial time verifier for this problem. Okay, so if you give me a decision problem A, right, then if it's possible to find such a polynomial time verifier with all of these properties, then A belongs to the set MP. Okay. If it's not possible to design a polynomial time verifier, okay, then A is not in the set MP. Okay, so MP is a set of all decision problems which have polynomial time verifiers. Okay, yeah, so this is a pretty complicated definition, so I'm going to give you lots of examples of this. But right now, are there any questions about this definition? Yeah, so like I know that the first time I saw this definition, I was completely confused by what they were talking about. Okay, so to make it less confusing, I'm going to give you lots of examples which hopefully clarify things. But right now, just in terms of the formal definition itself, are there any questions? So if you have any questions, just type it into the text box. All right, the fourth property, you're talking about 1, 2, 3, 4. If X is a no instance, so this is the one you're talking about? Is that the one you're talking about? Okay, yeah. So if I give you an instance X, it's either going to be a yes instance, meaning X has a solution, or it's going to be a no instance, meaning X does not have a solution, right? Okay, so when it's a yes solution, okay, then there is some sort of Y to make the verifier output 1. Okay, so basically, if there's a solution, then one thing I can do is I can show you the solution, right? So Y can just be equal to the solution. And then the verifier can just check that the solution is valid, right? And if it's valid, it'll output 1, right? Okay, but when you have a no instance, then there is no solution, right? So that means that if I give you any Y, okay, so Y is supposed to be a solution, right? But because there doesn't exist any solutions, then any Y I give you is an incorrect solution. Okay, so basically for any Y that I give you, the verifier is going to check this Y, and then it's going to see that Y is an incorrect solution. Okay, and then it's going to output reject. It's going to output 0. Okay, so that's what it means. Does that make sense? And any other questions about this? Okay, so yeah, so I'm gonna move on to some examples. If you have questions, just keep asking. Okay. All right. So before we do the examples, so what we need to do eventually is to show whether a problem is in the class P or MP. Okay. And to do that, basically, if you want to show that a problem is in the class P, then all you need to do is to find an algorithm which solves a problem in polynomial time. Okay, of course, that's easier said than done, right? Because if I give you a problem, maybe it's hard to find an efficient algorithm. Okay, but still, if you want to show the problem is in P, you have to give me a polynomial time algorithm to solve that problem. Okay. On the other hand, if you want to show that a problem is an MP, okay, so first of all, it should be a decision problem, right? Because it should be like a yes/no problem. Okay. We can also deal with like non-decision problems, but that's sort of more complicated. So let's just focus on decision problems. So if you want to show a decision problem is an MP, then you have to give a polynomial time verifier for the problem. Okay, so now you don't have to give an algorithm to solve the problem. Instead, you need to give a polynomial time verifier for this problem. Okay, and that verifier needs to satisfy all of these properties that we have. Okay. Yeah, and in terms of how you give the verifier, well, you have to first, so the verifier is some sort of algorithm. Okay, so you have to say what the algorithm does. Okay, and in particular, you have to say that if I give you some sort of certificate Y over here, right? What is the algorithm? What does this verifier do with the certificate and the instance? Okay, you have to specify the exact computation of that verifier. And if you can find such a verifier with all of the previous properties, then you've proved that this problem is an MP. Okay, so now, we're going to do some examples of these MP problems. Okay, all right. So the first problem we're going to look at is for coloring. Okay, so yeah, so now suppose I give you a graph. Okay, so previously we said that if I give you a map, right, then the map is supposed to be drawn on the plane. Okay, so if it's a planar map, then it's guaranteed to be four-colorable. Okay. However, now if I give you a general graph like this, and now what I require is that for every node, you give a color to the node. Okay, and furthermore, if two nodes are connected by an edge, right, like A and B over here, right, then they need to have different colors. If they're not connected by an edge, like A and C, then they can have the same colors. Okay. Right. And now the question is, if I give you some sort of graph, can you color this graph using only four colors? Okay. So for example, this graph you can color using four colors, right? But if I give you another graph, which is like this complete graph on 5 vertices, right? Then this you cannot color using 4 colors. Okay. You need to have more than 4 colors. You need 5 colors. Okay, okay, so this is the 4-coloring problem. Okay, and the claim is that this problem is in MP. And so how do we show that the problem is in MP? We have to give a verifier for the problem. Okay, so now I'm going to specify this verification algorithm. Okay, so the algorithm is going to take 2 inputs. Okay, it's going to take the X input, which is just a graph. Okay. And it's going to take another input, Y, and this is the certificate, and Y is supposed to represent an assignment of colors to the vertices. Okay, so if I give you a graph with, like, let's say 10 vertices, you have to give me, let's say, a vector of size 10, which assigns a color to each vertex. Okay, right, so that's the input for the verifier. Now, the way the verifier works is that it's going to go through several steps. Okay, so in the first step, it's going to check that this certificate Y you gave me uses at most 4 colors. Well, actually, even before that, it's going to check that this Y is an assignment of colors. Okay, so for example, if I give you a graph with 10 vertices, you need to give me like 10 colors to assign. Okay, if you give me like 5 colors to assign, right? So that means that you don't tell me the colors of all the vertices. You only tell me the colors of like half the vertices. Okay, then the verifier is going to reject right away. Okay, because you're supposed to give this verifier like either a solution or at least a hint to what the solution is. Right. So if I give you like a very incomplete solution, I give you just half the coloring. Right, then the verifier is going to say, no, okay, you got to give me like a much better solution or a much more complete solution. Okay. So first of all, the verifier is going to check that Y is a valid assignment of colors to all of the vertices. Okay. And then next, the verifier is going to check that Y uses at most 4 colors. Because we're trying to determine whether this graph can be colored using 4 colors. Okay. So if you give me a coloring with, let's say, 5 colors in it, right, then the verifier is going to output no immediately. Because, you know, if you give me a coloring with 5 colors, then this doesn't tell me whether the graph is 4-colorable. Right? I'm trying to figure out whether it can be done using 4 colors. And you give me a coloring with 5 colors, well, that doesn't help me determine whether you can do it using 4 colors. Okay? So if you give me a Y which uses more than 4 colors, then the verifier rejects immediately. Okay, then it just outputs no. Right, and then the next thing that the verifier does is that so first it checks that you use at most 4 colors. Okay, and then it goes through all of the edges of X, and then it checks that for the endpoints of each edge have different colors. So for example, if I'm given this this graph over here, and suppose Y represents this coloring that I'm showing over here. Okay. Then the verifier is going to go through all of the edges. Okay, like it's going to go through, it's going to go through this edge, right? It's going to check that, okay, the endpoints are different colors. Okay, it's going to go through this edge, it checks endpoints are different colors. Okay, and so on. It's going to go through all of the edges, and if all of the edges have different colors, okay, if this is true, if all of the edges, oops, what's this? Ooh, sorry about that. So I don't know what. Yeah, if all the edges have different colors, then the verifier is going to output 1. It's going to accept X and Y. Okay, and otherwise, if it ever encounters some edge where the endpoints have the same color, Okay, so for example, if this B here was colored red, okay, so when you check this edge, you see that, oh, these guys have the same color. Okay? Then the verifier is going to output no. It's going to reject. Okay, so that's how the verifier operates. Okay, it first checks that this Y, this coloring, uses at most 4 colors. Okay, if you use more than 4 colors, the verifier rejects. And then it's going to go through all the edges and check every edge has different color endpoints. Okay, if any edge has the same color endpoints, then the verifier rejects. And if all the edges have different color endpoints, then the verifier will accept. Okay, so that is the verification algorithm. Okay, so now let's check that this verifier satisfies all the properties that we require for these MP verifiers. Okay, so the two things, so the first two things we need to check are when X has a, so let's first consider the case where X has a solution. Okay, so X has a solution means that I gave you a graph and there is a 4 coloring for the graph. Right? Like for example, for this graph, okay, there is a 4 coloring for this graph. So if I give you this X, then and now I need to specify what Y is. Okay, so for example, Y can simply be this assignment of colors. Okay, and then if I give you this X and this Y, then when you run the verifier on this X and Y, you're going to see that okay, this is a correct coloring, right? Because you're going to go through all the edges. And you see that all the edges have different color endpoints. Okay, and so the verifier is going to output 1. Okay. Now the next case is where X does not have a solution. Okay, so for example, if I gave you this pentagon thing, right, as the input. Okay, so there you cannot 4-color this thing. Okay, and so that means that when I give you a Y, right, so Y is going to be some assignment of colors. Okay, so let's use numbers for the colors. Okay, so for example, I'm going to use these as my colorings. Okay, so suppose I give you this as my Y. Okay, then the verifier is first of all going to check that there are 4 colors being used. Okay, well, there are only 4 colors. Okay, so that's fine. Okay, but next, the verifier is going to go through all of these edges, and it needs to check that every edge has different color endpoints. Okay, so when it does this edge, this is okay, right? This is okay, and so on. But eventually, it's going to check this edge, and it's going to see that this edge has the same color endpoints, right? And so now the verifier is going to reject. Okay, and in fact, you can see that no matter what Y I give you, no matter what coloring I give you, okay, right? It's always going to reject. The verifier is always going to reject. Okay, because for example, if I give you this coloring, okay, so now I'm using 5 colors. So then the verifier is just going to reject at this point. Okay, at the very beginning, it's going to reject. Okay, and if I try to use 4 colors, then there's always going to be some edge with the same color endpoints in this pentagon. Right. So then the verifier is going to find that edge, and the verifier is going to reject. Okay. All right, and the final thing we need to check is that the verifier itself can run in polynomial time. Okay, and this is true because if we let n be the input size, and let's say the input size is just the number of nodes, okay, then this graph has order n squared edges, and so the verifier just needs to go through all the edges and check all the endpoints have different colors, and that's going to take n squared time. Okay, so therefore the verifier runs in polynomial time. Okay, and those are the 3 main properties we need. Okay, that when X has a solution, there exists a Y to make the verifier output 1. Okay, when X does not have a solution, then for any Y, okay, the verifier is going to output 0. And then finally, the verifier runs in polynomial time. Okay, and so because we have all these properties, then this shows that this 4-coloring problem is an MP. Okay, any questions about this? I have some more examples later, but any questions about this example? Okay, in that case, I'm going to I'm going to take let's say a 5-minute break. Okay, so let's break till 11:05, and then I'll continue with the rest of this. Okay. Okay, so let's continue. All right, so I want to go back a few slides to back to this definition of MP. Okay, so there's one thing I forgot to say, which is that you see in this definition of MP, when you have a yes instance, okay, we're saying that there should exist a y to make there should exist a y to make the verifier output yes. So now one question you might have is where does this y come from? Right? Like maybe is there an algorithm which produces this y or something? Right? Like because I haven't said anything about where this y comes from. Okay? And so in fact, the answer is that we don't care where y comes from. Okay? The only requirement is that there is such a y. Okay? You're not being so when you prove something is an MP, you don't have to say how you obtain this y in the case of a yes instance. Okay? The only thing you have to show is that there does exist such a y to make the verifier output 1. Okay, so for example, over here in this 4-coloring problem, right? So in this case, when there is a solution, then the y is supposed to be a assignment using 4 colors, which it's supposed to be a correct assignment, correct coloring using 4 colors. But we're not. I'm not asking you to. You're not required to produce this coloring. Okay. Your verifier only needs to check that if it's given this correct coloring, then it needs to say that okay, this coloring is correct. Okay. The verifier does not need to produce the coloring by itself. Okay. It only needs to check that a given coloring is correct or incorrect. Okay. So that's an important point. Okay, does that make sense? Okay, so so next we're going to do another example of an MP problem, and so this problem is going to be called factoring. Okay, so basically here I'm going to give you your input as an integer x, right? And then you just have to output. You just have to say whether x has a non-trivial factor or not. Okay, so for example, if I give you this huge number over here, this 999 something. Right? Then this can actually be factored into 2 big numbers, and so this would be a yes instance of the problem. Okay. If I give you another number like 7, right? So 7 is a prime number, so it cannot be factored. Then this is a no instance of the problem. Okay. Yeah. So okay. So now what we're going to show that this problem is an MP. So so again we need to give a verifier. And here, the verifier is going to take, one input is just going to be the number itself. And the other input, the certificate y, is also going to be a number. Okay. And the verifier is just going to check whether y divides x or not. Okay. And if it does, if x does divide y, so for example, if x is 10, okay, and if y is 5, okay, so, right, then the verifier is going to output 1. Okay, and otherwise, if I give you like y equals 3, right, then 3 does not divide into 10, and so the verifier is going to output 0. Okay, so it's a very simple verifier. You give me an x and a y, and I just do x divided by y. Okay, if that's an integer, I'm going to output 1. If it's not an integer, then I'm going to output 0. Okay, oh, and also a y cannot be 1 or x itself. Okay, so yeah. Okay, so let's check that this is a valid verifier. Okay, this verifier satisfies all our properties. Okay, so so the first part is that when x has a solution. Okay, so if x has a solution, for example, this x, right, then this means that x is a composite number. Okay, so x has at least 2 non-trivial factors, right? And so so here you can just make y any of the non-trivial factors. Okay, so for example, you can set y to this. So x is going to be equal to this number, and y is going to be equal to that number. And when you divide x divided by y, you're going to get a, you get an integer, which is not 1. And so you're going to output 1. So whenever you have a composite number, you can just give one of the factors of that composite number as the certificate. And that's going to make the verifier output 1. Okay. On the other hand, if x does not have a solution, okay, then this means that x is a prime number. Okay, so for example, if I give you x equals 7, okay, then if you give me any y, okay, then either your y is going to be equal to 1 or to 7, right, in which case I'm going to reject. Okay, or if you give me any other number, then it's not going to divide into 7. Okay, like if you give me 3, right, I'm going to check 7 divided by 3 is not an integer, so then the verifier is going to output 0. So for any y you give me, okay, which is not equal to 1 or 7, the verifier is going to reject. Okay. Yeah. Okay, and the final condition is that the verifier has to run in polynomial time. Okay. And this is true because the only thing the verifier does is it divides, it computes x divided by y, okay, and that takes polynomial time. Okay, so therefore we've shown that this factoring problem is an NP. Now, on the other hand, even though this problem is an NP, this problem does not seem to be in P, okay, because if you want factoring to be in P, then what you need is that if I give you an input x, okay, then you need to find all the factors. So for example, if you want to show factoring is in P, then if I give you this huge number over here, right, you got to find these two factors for me. Okay. And we actually don't have any efficient algorithms to factor large numbers. Okay, basically, if I give you this huge number over here, the way you find factors is you might just try all smaller numbers and you just divide into this huge number. Okay, but as you can imagine, that's going to take a huge amount of time. Okay, it's not a polynomial time algorithm. Yeah, so this is an example of a problem which is in NP, but it does not seem to be in P. However, we also cannot prove that factoring cannot be done in polynomial time. Okay, we currently don't have any efficient algorithms to factor, but that doesn't prove that there doesn't exist any such algorithms. Okay, oops. All right, so the next problem, so the next problem is called traveling salesman. Okay, so we're gonna see that this problem is also in NP. Okay, so the problem is that suppose I give you a graph. Okay, so for example, all of these blue vertices. Okay, and then the graphs have some sort of edges between them, which I didn't draw all the edges. Okay, but there could be some like additional edges, like or actually yeah. So there could be some additional edges. Okay, like this. Okay, but anyways, so each of these edges has a weight or a distance on it. Okay, so this could be like distance, like 10 here, and this could be like 5, and this one could be like 7 or something. Okay, all right. So you have this weighted graph, and now what you need to do is to find a path through this graph which goes through all of the vertices. Okay, all of the vertices exactly once. Okay, so for example, you can see this path goes through all of the vertices exactly once. Okay, and furthermore, the sum of the distances on this path. Okay, so for example, this is 10, and this is like 2, and this is like 2, and then 6 or whatever, right? So if you add up all of these numbers, okay, then the total has to be less than d for some given d. Okay, so if I give you like 1,000, okay, can you go through all these points using distance less than 1,000? Okay, so the claim is that this problem is also in NP. Okay. Right, so we're going to give a verifier for this problem. Right, so the verifier, the first input x is just going to be the weighted graph itself. Okay. The other input y, the certificate, is going to be a path through the graph. Okay, and what the verifier does is it checks that this y actually goes through every vertex once. Okay, because this is one of our requirements. You have to visit every city exactly once. Okay. And furthermore, it checks that the total length is less than or equal to d. Okay. If both these conditions are true, the verifier is going to output 1. And otherwise, it's going to output 0. Okay. All right, so now let's check that this verifier is valid. Okay, so the first thing is that suppose x does have a solution. Okay, so if x does have a solution, then this means that there does exist this path that goes through every city once, right, and has distance at most d. Okay. So in that case, let's just say, let's call that path y. Okay, and then I'll just give y to the verifier. Right? So when you give y to the verifier, then the verifier is going to check that, okay, y does in fact go through every vertex. Okay, and the total length is in fact less than d. And so therefore the verifier outputs 1. Okay, so when x has a solution, it is possible to make the verifier output 1. Okay, on the other hand, if x does not have a solution, okay, so what does this mean when x does not have a solution? This means that you have a graph where no matter what path you choose, okay, either this path is not going to go through every city once, or the path has length larger than d. Okay, that's what it means for x not to have a solution, right? Okay, so in that case, this means that any y that you give to the verifier, okay, so the verifier is going to interpret this input y as a path, okay, and then it's first of all going to check that this path goes through every vertex once, okay. So either the input y does not go through every city once, okay, or the input or the y has length more than 10. Right, because we said that no matter which path you choose, okay, this path has to have one of these two properties. And so when the verifier does its job over here, right, it's going to see that one of these two properties it's checking for is not satisfied, and so therefore the verifier is going to output 0. Okay. Any questions about that? Okay, and then the final thing we need to check is that this verifier is going to run in polynomial time. Okay, and this is true because all the verifier does is it just it does this this check over here. Okay, so it just goes through every vertex of y, right, and then it adds up the total length of that path. Okay, so this path y has to have n vertices. Right? Otherwise, it's not going through all the vertices. Okay, and to add up all the distances, it just takes you order n time. So therefore, the verifier runs in polynomial time. Okay, so that shows that the this traveling salesman problem is an NP. Okay, so so we're gonna do just a few more examples. Okay, so maybe you guys are like sort of getting the hang of this, but we'll just do a few more. Okay. And also, the reason we're going through some more problems is because we're going to use these other problems later when we study NP completeness. Okay, so I'm just going to define all of these problems now so we can reuse them later. Okay, so the next problem is called the K-clique problem. Okay, and here, again, it's a graph problem, and you're given, let's say, this graph. Okay, and now you want to find a clique in this graph, where a clique is just a set of nodes which are all connected to each other. Okay, so for example, if you take, let's say, these 3 nodes, okay, so they're all connected to each other, so they form a 3 clique. Okay, if you take these 5 nodes over here, they're all connected to each other, so they form a 5 clique. Okay, and if you take, how many nodes are there? There are 7 nodes over here, right? So these 7 nodes are all connected to each other, so they form a 7 clique. Okay. So now the question is, if I give you a graph and I give you a number k, right, whether it's like 3 or 4 or 5 or whatever, okay, is there a k clique in this graph? So for example, if I give you k equals 7, okay, then you can say that yes, there is a 7 clique in this graph. But if I give you the number 8, right, then I think there's no 8 clique in this graph. I don't think you can find 8 nodes which are all connected, right? Yeah, so in that case, you would say that no, there is no 8 clique in this graph. Okay, yeah, so the input to this graph is just, the input to this problem is just a graph and the number k, and you have to say whether or not there is a k clique. Okay, so now we're going to show this as an NP, and the first thing to do is to describe the verifier. So the verifier is going to, so the certificate that the verifier receives, in this case, it needs to be a set of k nodes. Okay, and then the verifier is going to check that every pair of these k nodes is, it's going to check that these k nodes are all connected to each other. Okay, so for every pair of these k nodes, the verifier is going to check that they have an edge between them. Okay, and if that's true, it's going to output 1. Okay, and otherwise the verifier outputs 0. So for example, if I'm using this graph and I want to find a 5 clique, right, then I can give this set of 5 nodes to the verifier. Okay, and then the verifier is just going to check that, all these nodes are connected to each other, right? It's going to check all these edges between these 5 nodes, and it sees that they're all connected, so it outputs 1. Okay. On the other hand, if I gave, let's say, some other set of 5 nodes, okay, if I gave these 5 nodes to the verifier, right, then it'll again go through all the pairs of nodes and see whether they're connected, and it's going to see that these 2 nodes, for example, are not connected. Okay. In that case, it's going to output 0. Okay. So what that shows you is that you need to give a good Y. You need to give a good certificate to the verifier. Right? In this case, if I give the good certificate, it'll make the output 1. If I give a bad certificate, it'll make the output 0. Okay, but this is but this is okay because the requirement is that when X has a solution, there exists a good certificate. Okay, so in fact, there does exist a good certificate, that one. Right? I mean, it's fine if there are also bad certificates. Okay, so this is a bad certificate, and that's fine. Okay, as long as there's at least one good certificate when X has a solution, then we're okay. All right. So the other thing we need to check is that when X does not have a solution, okay, then the verifier has to always output 0. Okay, and the reason for this is that if there is no solution, then for any set of k nodes that you choose, there's some 2 nodes which are not connected. Okay, so for example, suppose I'm trying to find an 8 clique in this graph. Okay, so we know that there is no 8 clique. So if I give you let's say I give you these 8 nodes, okay, then you're going to go through all of them and you're going to see that, oh, these 2 guys are not connected. So then the verifier is going to output 0. Okay, so you can see that in this graph, because there is no 8 clique, then for any set of 8 nodes you give the verifier, it's going to find that some 2 of them are not connected, and so it will output 0. Okay, so we satisfy the second property for the verifier. And the final property is that the verifier needs to run in polynomial time. Okay, and this is true because the input to the verifier is just a set of k nodes, right? And the verifier is going to check that all the nodes are connected, and that just takes k squared time. Okay, so it runs in polynomial time. All right, any questions about this one? Okay, so the next thing we're going to do is that we're going to show that all problems. So far we've shown that a bunch of these individual problems are in MP, right? And the next thing we're going to do is we're going to show that any problem in P is also in MP. Okay, right? So P is like a collection of problems that you can solve in polynomial time, and MP is some other collection of problems. Okay, so what we're saying is that anytime you can solve a problem in polynomial time, right, then this problem is also in MP. Okay, and so to prove this, what we're going to do is suppose A is a problem in P. Okay, and so that means that there is a polynomial time algorithm, let's call it S, which can solve A. Okay, meaning that for any instance x of A, when x has a solution, S is going to return the solution. And when X does not have a solution, then S is going to return fail, okay, because to indicate that there is no solution, right? Because A is solvable in polynomial time, so so there has to exist such an algorithm S which does this. Okay, right. And now using this, we're going to construct a verifier. Okay? And so the verifier is just going to run this algorithm S. Okay, and if S finds a solution, the verifier is going to output 1. And if S does not find a solution, then the verifier outputs 0. Okay, so now let's check that this verifier works correctly. Okay, so when X has a solution, okay, then we know that when you run S, right, it's gonna find the solution. Okay, so the verifier is gonna output 1. Okay, now in this case, notice that the verifier doesn't even require any sort of certificate, right? In fact, there's no Y here, right? We haven't said anything about Y. Okay, yeah, so. All right, and in the next case, where X does not have a solution, right, then when you run this algorithm S, it's going to return fail, and so the verifier is going to output 0. Okay, and finally, the verifier is going to run in polynomial time, right, because all it does is it runs S, which itself runs in polynomial time. Okay, so that shows you that for any problem in P, there is a polynomial time verifier for that problem. And so that means that all problems in P also belong in MP. Okay, and one more thing is that for these problems in P, okay, as we said, we don't even need a certificate Y to help the verifier, right? Because what happened is for these more difficult problems like clique and traveling salesman and these other difficult problems, right? The verifier itself couldn't determine, for example, for clique, okay, the verifier, if you don't give it a certificate of K nodes, okay, then the verifier itself cannot actually find these K nodes. So it doesn't know whether or not there exists K nodes which are connected. Okay. So that means that in order to help the verifier, you have to give it the certificate to help the verifier. Okay. And this is because this clique problem is very difficult. Right? We don't know how to efficiently find K nodes which are connected. But on the other hand, for these P problems, right? So once you go to P, then these problems are very easy, right? Because they themselves can be solved by this polynomial time algorithm S. Okay? So in this case, the verifier doesn't need any help, okay? Because the verifier can just run the algorithm S, which is efficient, and the verifier itself can efficiently find the solution. Yeah, okay, right, and yeah, so for hard problems, right, V itself cannot find the solution. So therefore, it needs to be given this certificate or hint. Yeah, so for example, in factoring, right, if you just have the verifier, right, the verifier itself doesn't know how to find a non-trivial factor. Okay, so you have to give the verifier this hint, right? You have to give it one of these factors, and then the verifier can say, oh, okay, this is a correct factor, right? So in that case, all the verifier needs to do is just divide the number, and that's easy to do. Okay? It doesn't need to actually find the factor, which is very hard to do. Okay, all right, so so one more, oh, okay, well, actually, all right, so another problem, okay, so this one is just to show you that, so up to now, all of these MP verifiers we gave were pretty straightforward, right? Because basically, whenever you're given a problem, then the verifier just expects to have a solution to the problem as the certificate, right? Like if I give you a graph, if I give you this K-clique graph, right, then the certificate that the verifier wants is just sort of the solution to this problem, right? It wants K nodes which are actually connected. Okay, and so in that way, it's sort of pretty easy to prove that a problem is an MP, right? Because you just need to check whether the solution is correct or not. Okay, but this is not always the case. Okay, because there are some problems which are in MP, but the certificate you need to give the verifier is not the solution itself. Okay, you need to give it some sort of abstract representation, some indirect representation of the solution. And in that case, it might be harder to figure out, which kind of abstract representation should you give to the verifier. Okay? So as an example of this, we're going to show that primes, this problem, okay, is an MP. Okay, so the problem simply is that if I give you a number, is x prime or not? Okay, so this is different from the factoring problem we looked at, because in factoring, the yes instance, so for this factoring problem, okay, I give you a number and you have to say whether it's composite or not. It's non-prime. Okay, and for prime, you have to say whether it's prime or not. Right, so prime is like the opposite of factoring. But it turns out that if you have a problem which is in NP, the opposite of that problem may or may not be in NP. Okay, so just because you know one problem is in NP, if you flip that problem, okay, so you make all the yes instances into no instances and then vice versa, right? So you flip that problem into the opposite problem, you're not guaranteed that this opposite problem is also in NP. Okay, so even though we know factoring is an NP, that doesn't guarantee that prime is an NP. Okay, we need to separately design another verifier to show that prime is an NP. Okay, all right, so let's try to design a verifier to show that prime is an NP. Okay, so then actually I'm not going to give you the verifier. Okay, the verifier is kind of complicated. Okay, but what I'll do is I'll show you that these simple verifiers that we've tried previously, where the verifier just checks a solution is correct or not. Okay, these simple verifiers are not going to work. Okay, so therefore, to prove that primes is an NP, you have to give a more sophisticated verifier. Okay, which I will not do for you, but I'll tell you how to I'll tell you where to look for that verifier. Okay, all right, but let's see that if you try a simple verifier, this is not going to work. Okay, so for example, let's try to build a simple verifier, and what should our certificate be? Okay, so let's how about we can try to make the certificate just be a single number which does not divide the input x. Okay, so if I give you x is like 10, right? Then if you give me 3, right? Right, this shows that okay, 3 doesn't divide into 10. Okay, but it doesn't prove that there are no numbers that divide into 10. Right? Because you just gave me one single number which doesn't divide into 10, but there could be other numbers which do divide into 10. Okay? All right, so therefore this verifier is not correct. Okay? If the verifier just checks a single number, then this is not a correct verifier. Okay? All right, so then let's try something else. Okay? Let's try, suppose I give you, actually, let me make x be something else. Okay, let's make x equals 7, okay? Right, so suppose, let's try this, okay? So now we have a different verifier, and now y is not just gonna be a single number, okay? It's gonna be a vector of numbers, okay? And the vector of numbers is just gonna be x divided by y for every single value less than, let's say, the square root of x, okay? So actually, let's make this guy 11 over here, okay? All right, so in this case, y would be equal to, let's say, a vector. So then we would try, 11 divided by 2. Okay, so that's like 11 divided by 2, right? We try 11 divided by 3, 11 divided by 4, right? And now these are all of the divisors up to the square root of 11, right? We've tried all possible divisors up to the square root of 11. And there's this theorem that says that if all of these numbers do not divide 11, okay, if you take every single number less than the square root of 11 and none of them divide into 11, then 11 is a prime. Okay, all right, so then if I use this y as my certificate, okay, then this is a, whenever x is prime, then y will prove to me that x is prime. Okay, because y, all of these numbers will be non-integers. And that proves that x is not prime. Okay, so in this case, there does exist a y to make the verifier output yes. Okay, right? If I just give it all these numbers, the verifier is going to check that all of these numbers are not integers, and that proves that x is prime, and the verifier can output yes. And on the other hand, if for example, x equals 10 here, right? So then if I give it, so then here I would give it, 10 divided by 2, right? 10 divided by 3 and 10 divided by 4. And then the verifier would see that one of these is an integer, right? And then it would output no. Okay? Yeah, so in this case, the vector y can correctly indicate to the verifier whether or not x is prime. Okay, so yeah, so then this, or sorry, I should have shown you this part. Okay, so this seems to be a correct verifier, right? Because when x has a solution, right, then the verifier is going to return 1, and when x does not have a solution, the verifier returns 0. Okay, so far so good. Okay. But the problem is that this verifier does not run in polynomial time. Okay, and the reason is that suppose your input has n digits. Okay, then they're about 2 to the n over 2. Let's say they're binary digits. Okay, yeah. So x, the size of x is approximately 2 to the n. Okay, and so that means that there are about 2 to the n divided by 2 numbers less than the square root of x. Right? Okay, and in that case, I'm gonna have to in that case this list y I give you. Okay, how large is that list? Well, I'm gonna have to divide x by I need to divide x by all of these numbers. Okay, x divided by 2, x divided by 3, and so on, all the way up to x divided by root x. Okay, so in total, there are going to be about 2 to the n over 2 of these numbers, and each of these numbers has about n digits in it. So therefore, the size of this y is going to be this. Okay, so now y has exponential size. Right, the size of y itself is exponential. Okay, and then the verifier has to go through all of these numbers and check all the values. So the verifier needs to take exponential time. Okay, so the problem with this verifier is that it does not run in polynomial time. Okay, it correctly outputs these accepts and rejects, but it takes too much time. So this shows that this second verifier, okay, so the first verifier is not correct, and the second verifier is also not correct. Okay. All right. So far we've failed to show that primes is an NP. Okay. However, you know, in fact, primes is an NP problem. Okay. So there does exist a verifier to which satisfies all these properties we want. Okay. And yeah, and so that verifier is kind of complicated. Okay. It's not one of these simple verifiers that we've seen up to now. Okay. In fact, the verifier has a name. So this is called Pratt's theorem. Okay, which shows that primes is an NP. Okay. So if you're interested, you can go look up this this result. Okay, to see to see how this works. All right. So any questions about any of this stuff? Okay. So up to now, we've seen that we've seen the definition of NP. And we've seen lots of examples of how you prove something is an NP. Okay, and sometimes it's pretty straightforward to give the verifier, but there are cases where it's not so easy to give the verifier. Okay, so any questions about anything? Verify is an algorithm, but what is this certificate? Okay, yeah, so the certificate is actually not an algorithm. Okay, so the certificate is a string. Okay, it's basically like a piece of data. Okay, so for example, let's go back. Let's do a few examples. Okay, so here the certificate is just a set of k nodes, right? So it's just you just specify k nodes, right? So I'm not saying like how you found the certificate. Okay, we don't care how you find the certificate. Okay, you just need to as long as there exists k nodes, then you're gonna give those k nodes as the certificate to the verifier. Okay, so as another example, so this traveling salesman example, okay? So here the certificate is just a path through the graph. Okay, so again, that's just like a piece of data that you provide to the verifier. Okay, does that make sense? And this data usually represents the solution, okay? But as we said, in the primes case, sometimes you cannot just directly use the solution as your certificate. You have to use something more clever as your certificate. Okay. So whether it's correct or not. What's the full question? VW. I think certificate is like an answer. Yeah. So certificate is usually like an answer. Okay. Because for example, in the TSP case, right, it exactly is the answer. Okay. It's just this path which solves TSP. Okay, and likewise in Clique, right, it's also the answer. Okay, it's just these k nodes. Okay, but the problem is that for some problems which are in NP, right, you cannot just give the answer directly. Okay, so for example, this do this again, okay? Yeah, for example, for this this primes problem, okay? What is the answer to this primes problem, right? You have to somehow give me like some numbers which prove to me that a number is prime, okay? This is hard to do, right? I mean, if I'm asking whether a number is composite or not, right, then you can just give me a single number, which is just any non-trivial factor, and that proves this number is composite. Okay. However, if you want to prove a number is prime, then you have to show that for all possible numbers, if you divide into this prime number, you get a non-integer, right? And so now, you know, like the answer would be that, you know, the straightforward certificate would be that you give me all of these numbers and you divide them into this prime number, and you see that all of them are not integers. Okay, so that is this solution that we talked about over here. Okay. But this is not a valid certificate because the certificate is too big. Okay, it has exponential size. So you cannot verify the certificate efficiently. Okay, so instead you need to give some sort of very small certificate which has polynomial size. And when you check this certificate, you can still be guaranteed the input is prime. Okay, but it's not clear what that certificate is, right? Like we need some like mathematical tricks to design that certificate. Okay, which is why proving primes is an MP is a more difficult problem, right? So yeah, so if you want to see how to do it, you can look up this theorem over here. Yeah. So, anyways, in answer to your question, usually the certificate is an answer. Okay, but it's not always a direct answer. It's sometimes a very indirect answer. Okay, does that make sense? Any questions about this? If it means certificate is assumed to be given, although itself, yeah, exactly, right. So we don't know where this certificate comes from. Okay, the requirement for MP is that there exists a certificate. Okay, you don't need to specify where it comes from. Okay, so in fact, it's usually very hard to get that certificate. Right. So, for example, for the clique problem, right, our certificate was the set of k nodes, which are all connected. Right? But we don't know how to find those k nodes. Right. So we have no way of efficiently constructing this certificate. Okay. But for MP, all you need to do is to say that there exists this certificate. You don't need to say how to construct it. Okay. Yeah, right. This exactly right. This thing over here, right? This is exponential. That's right. This is not poly. Okay. Did I say it's poly? Yeah. Well, I'm saying that it does not run in polynomial time. Okay, because you know, the certificate has this exponential size, and to check that certificate, you also need exponential time. Yeah. Okay. Any other questions? I mean, so it's great that you guys are asking questions because, again, this MP concept is very sort of tricky. It's kind of convoluted, right? It's like, yeah. So then if you have any questions, just keep asking, and then we'll try to clarify all of them. All right, so then I'm gonna do one more thing before we talk about something else, which is I'm gonna show you some incorrect verifiers. Okay, so up to now I've shown you a bunch of like correct verifiers for these problems, but when you design verifiers yourself, you need to be careful about certain things. Okay, so to show you what you need to be careful about, I'm gonna give you a few examples of incorrect verifiers. Okay, all right, so we're gonna go back to this. Wait, so no, it's not poly. Yeah, right. Yeah, so we're going to go back to this k-clique problem. Okay, so again, I give you a graph, and you need to find k nodes which are all connected. Okay, so we already showed a correct verifier for this problem, right? But now let's see some incorrect verifiers. Okay, so in the future, you want to make sure to avoid all of these types of problems. Okay, and so when you give an incorrect verifier, okay, that does not prove that this k-clique problem is an MP. Right? To prove that k-clique is an MP, you have to give a correct verifier, which can either be the verifier that we showed previously or maybe some other verifier, but these examples I'll give you are not correct verifiers. Okay. All right. So like the first verifier is suppose you just have this very naive verifier. It's always going to output 1. Okay. No matter which certificate you give it, it's always going to output 1. Okay. Now, why is this not correct? Okay. So we have these 3 conditions, right? When there is a solution, there is some certificate to make the verifier output 1. Okay. Now, this verifier actually satisfies the first condition, right? Because when you give it a graph which has a solution, then because the verifier always outputs 1, then it will output 1. Okay. However, it's going to fail the second condition. Okay. The second condition is that when there is no solution, okay, when there is not a k-clique in this graph, then for all certificates, the verifier is supposed to output 0. Okay, but here the verifier keeps on outputting 1. Okay, so this is incorrect. So this verifier does not work. Okay, all right. Another verifier is, well, what if it always outputs 0? Okay, no matter what the certificate is, the verifier always outputs 0. Okay, so now the verifier satisfies the second condition, which is that when you get a no instance without a k-clique, then no matter what certificate you have, the verifier always outputs 0. Okay, now our verifier does satisfy that property because no matter what, it's always going to output 0. Okay, so it satisfies property 2. But it fails property 1 because property 1 says that when there is a k-clique, okay, there is some y to make this verifier output 1. And in our case, there's no y to make this verifier output 1 because it always outputs 0. Okay, so the verifier fails the second condition, the first condition. Okay, and the third incorrect verifier is that, well, suppose you have a verifier which checks all, so I give you a graph with like n nodes, right? And the verifier is going to check all subsets of n nodes. Okay, if any of these subsets of n nodes forms a clique, it will output 1. Okay, and otherwise it's going to output 0. Okay, now this verifier is going to satisfy the first 2 conditions. Because if I give you a graph which does have a k-clique, right, then this verifier is going to check all possible subsets, and it will find that k-clique and output 1. Okay, so it is possible to make this verifier output 1 when there is a k-clique. And when there is not a k-clique, right, then this verifier checks everything and sees that nothing is a k-clique, and it will always output 0. Okay, so this verifier satisfies the first 2 conditions. However, it does not satisfy the third condition, which is that the verifier needs to run in polynomial time. Okay, because this verifier is going to check all subsets of k nodes, right? And that's going to take you basically n to the k amount of time. Okay, and here k is not a fixed number, right? K is part of your input, right? Like if I give you a graph with 100 nodes in it, right? I can ask k to be like 2. Or 10 or like 50. Okay, so here k is part of your input. So depending on the value of k, you need to take n to the k time, and this is not a polynomial because for a polynomial, k needs to be a fixed number. Right here, if I make k large, then you need to take more time. Okay, so therefore this verifier is not a polynomial time verifier, and so this is also incorrect. Okay. All right, so I guess we don't have much time here. So I'm just going to get started on the, so I guess I'll just, what am I going to do? Let me see, what else do I have? So, okay, yeah, so I'll just get started with the next part, okay? So we've finished talking about MP, basically. Well, not exactly, but anyways, we've at least introduced, or we've talked about how to prove things are in the class MP. Okay, so the next thing we want to do is to talk about this class of MP complete. Okay, it's a different set of problems. Okay, but before we do that, let's talk about this very famous problem called P versus MP. Okay, so this is probably the most famous problem in computer science. And what this problem means is that, so P is a set of problems, and MP is another set of problems. Okay, so this P versus MP problem is asking, is every problem in P also in MP? And vice versa, is every problem in MP also in P? Okay, so if P equals MP, right, then we have to have both conditions being satisfied. Okay. All right, yeah, so okay, so the first thing is like, why do we care about this problem? Why do we care about P versus MP? Okay, because as I said, it's probably the most important problem in computer science. Okay, I mean, the other big problem would be to have like some sort of general AI. Okay, that would also be, maybe more important. Okay, but this is, one of the most important problems. Okay, but why is it so important? Okay, it's because there are many real-world problems which are in MP. Okay, so for example, this clique problem that we talked about. Okay, this has many applications, right? For example, if your graph represents like a social network or something, okay, you might want to find whether there are 10 people who are all friends with each other, okay, or 20 people who are all friends with each other, okay, or you might ask, what is the largest number of people who are all friends with each other? Okay, so those are all clique problems. Right, the factoring problem, okay, if you can solve that factoring problem, then you can basically break a lot of cryptography that we use nowadays, because a lot of cryptographic functions are based on factoring. Okay, so if you can solve factoring efficiently, if factoring is actually a P problem and not just an MP problem, then you would basically break a lot of the cryptography that's in use today. So there are many real-world problems which are in MP. And if it turns out that P is equal to MP, then that would mean that all of these MP problems can also be solved by a polynomial time algorithm. So they can be solved efficiently. Okay? And so that would both have good consequences and bad consequences. Okay, good consequence would be like you can solve clique efficiently and find these big cliques on social networks, for example. Okay, bad consequence would be that you can break cryptography, and now you can't transfer money securely. Okay, so if P equals MP, there's like a huge number of consequences for computer science. Okay. And on the other hand, if P does not equal MP, okay, then that would mean that there are some of these MP problems where it is not possible to solve them efficiently. Okay, so in that sense, it would almost be like a good thing, because, for example, if you can show that factoring is not a P problem, then that would mean that it's not possible to efficiently factor. Okay, and that would mean that our current cryptographic systems are secure. Okay, at least against like normal computation and not like quantum computation or something. Okay. Yeah, so both P equals MP would have many consequences, many important consequences, and P not equal to MP would also have important consequences. Okay, all right. So then what's the answer? Okay, is P equal to MP or not? Okay, well, we know part of the answer. Okay, because we know that every P problem is an MP, right? We proved that. Okay, so this was what. Let's go back. Oops. Right. So here's what we said. Okay, all problems in P are in MP. Okay, so we know half of the answer to P versus MP. Okay, but the other half is much more difficult. Okay, which is that is every MP problem in P? Okay, this is much more difficult. So in fact, people so they started thinking about this problem probably back in the 1970s. Okay, that's when this theory about MP completeness got developed, and so it's been about 50 years now, and nobody knows the answer. Okay. Most people think that that there are MP problems which are not in P. Okay, so for example, all of these previous problems I talked about, well, not all of them, but many of these previous problems like clique and TSP. Okay, people think that these are MP problems which are not in P. Okay, and factoring, okay, is also something that is an MP, but we currently don't know how to do it efficiently in P. Okay. But nobody has a proof for this fact. Okay, nobody can prove that there are MP problems which are not in P. Okay, so if there are MP problems which are not in P, then that would mean that P is not equal to MP. Right? If you can prove either way, okay, if you can either prove P equals not equal MP or P equals MP, right? Then, well, first of all, you get $1 million, okay, because there's this thing called the Clay Math Institute, and they propose these 7 problems called the Millennium Problems, and they're like very difficult math problems, right? Like the Riemann hypothesis. And if you can solve any of them, you get $1 million. Okay. But probably more importantly, you're going to go down in science as one of the truly great scientists of all times. Okay, like because not only does this P versus NP problem have many real world consequences, the thing is that currently, nobody has any idea how to solve this problem, and it's probably because the techniques that we're using to look at this problem are just wrong. Okay, like we're taking the wrong approach to looking at this problem, right? Just kind of like you could say, we're taking the wrong approach to solve AI right now using like deep learning, right? Maybe that's not going to solve AI. Okay, so for this P versus NP, the current approaches that we have do not get anywhere close to solving this problem, right? And we don't have any better solutions. So in order to solve this problem, you need to have a completely new way to think about this problem, okay? And we don't have anything resembling that right now. Which is why sort of I'm making this claim over here that if you can actually come up with this completely new, profound perspective on how to look at computations, then that really does make you one of the most important scientists in history. Okay, so anyways, so that is why we care about this P versus NP problem. And so I guess next time we're going to talk about what NP completeness is. Okay, so this is a theory which was developed to try to answer the P versus NP problem, right? As I said, it's not been successful so far, but it's our best